Hi, welcome back. Today we're doing problem number 1483, kth ancestor of a tree node. And this problem is quite difficult, I'd say, and it teaches you an algorithm that I would say most people don't know, and also you learn a little bit more how logs work, a little bit better than you would, hopefully, at the end of the video. So let's just do a little brief overview of the video. You're basically given a tree with a number of nodes, and they're initialized 0 to n. So here there's a balanced tree, but you're not necessarily given a balanced tree. It can be any kind of tree. And it's asking, given a node and a k, return the k ancestor of a node. If it doesn't exist, return -1. So for example, if we're given node 3, and we're asking return the kth ancestor, we just go up 1, so this would be the parent. If we were given the second ancestor, we would have 0. If we're given the third ancestor, we'd have -1 because it doesn't exist, and so on. And this is a balanced tree, but it doesn't have to be balanced. And so the first way you can think about doing this is you can just store this array of all the parents. And then you can just say something like, while k is greater than 0, just keep giving me the next parent. So for example, if we are at, let's just print this array real fast, give an example. Okay, so let's say we are at this array. It's 1, 0, 0, 1, 1, 2, 2. Okay, and let's say we're given something like, okay, give me 3, node 3, k2. Well, we could just say, okay, let's just take the parent k times. So we go to node 3, so 0, 1, 2, 3. All right, the parent's 1. Now let's go to node 1. Okay, the parent's 0, so 3, 2 would be 0. And so on. But also, you got to keep in mind that our tree, so in this case, it's balanced. But what if our tree is something like this, right? 1, 2, 3, and so on. Then to get to the kth ancestor, let's say we have 1,000 nodes and we want 1,000th ancestor, we'd have to go up 1 by 1 by 1 by 1 by 1. So the time complexity of getting k equals k worst case. Or it just is, yeah, so it's k worst case because let's say we're asked to get k of 1,000 on this tree, we would just go out of bounds. So here it would only be 2. But if we are given a linear tree and we want an ancestor, we have to go up k. And let's say, so k is how long it would take to get k. And then if q, let's call q a query that we're asked. So every time we're asked get kth ancestor, that's q. And let's say we're asked that q times. And I think they tell us there will be at most 5 times 10 to the 4 queries. So you're given 10,000 queries, and 10,000, this k can be a 10,000. So 10,000 times 10,000 is going to be in the millions, and that's going to be n squared complexity. Also, by the way, so another good hint for LeetCode problems is you can read the constraints, and instead of just trying something and having a time limit exceeded, also, I guess you can probably figure out that for a hard problem, it's not going to be as simple as just iterating through this array k times. But if you're given some kind of queries, and let's say you're given 2 numbers, like a k and an n or something, and your k is really small and your n is really big, you want to use these constraints and figure out, okay, what am I modifying? And if the number is small, then I can use something that's n squared or some kind of backtracking or, things like that. And there's always going to be a trade-off between time and space, so you do always want to look at the constraints and how big they are and try to figure out how efficient your solution can be. Because, for example, if the most queries you're ever given, or let's say your k can only be to 10, and then your q can only be 10 as well, there's no reason to come up with some super efficient solution that only gets called 1,000 times max or 100 times max. It doesn't make any sense. So that is one thing to know. And also, by looking at these constraints, you can kind of get a hint at what it's the algorithm I'm going to be using. And so let's think of another algorithm. Is there another way we can get these ancestors in a more efficient way than just going up k times? Well, so let's draw this tree, and let's draw a few more nodes here. 6. So I'll just draw this many nodes. Okay. And so for these nodes, is there any way of, let's say, we can figure out the root of 12, let's say, like if we want 1, 2, 3 or whatever, instead of going up by 1? So what we could do technically, which would give us the highest space complexity, is we can just store for every node an array of its parents, right? So for something like 12, we can just go to every node and literally just go up. So we could do this, go up, and then we store an array of its parents. So it would be something like 5, 2, 0. And then we can say, okay, well, if we have k and k is bigger than this array, then we return -1. Otherwise, return some index. So let's say it's k2, we can do that. But we'd have to do that for every single node in the tree. And also, there are 10 to the 4th nodes. So that's also not the greatest idea because we're going to have n squared space complexity now, which is also not ideal. So is there anything else we can do? Well, can we figure out the parent, or let's say we want to get the second node from 12. Well, can we do that if we have the parent of this node? So if we want to get, if k is 2, can we get the second ancestor of this if we have the ancestor of this? Well, yeah, we could go up 1. So the algorithm we're going to be doing, and it is kind of confusing, it's called binary lifting. And basically what it does, instead of storing every single parent, we can just store incremental ancestors. So we can store something like a log order of ancestors. So let me show you what that looks like. Okay, so let's say for this 12, instead of storing 520, we store a logarithmic order, and it would actually be better to demonstrate that if we have this long tree again. So let's just say we have 0, 1, 2, 3, 4, 5, 6. So let's have a tree like this, because then we have more parents, and let's just say that these nodes are all connected. Okay. So what we would store is we would have the first parent of 8, which would be 7. Then we would store, instead of storing the next one, we want to store the next logarithmically higher one. So it would be something like the 2 to the 0 parent, then the 2 to the 1 parent, the 2 to the 2 parent, so on. So 2 to the n. So when n is 0, it would be 0, or it would be 1. And then 2 to the 1, we would store 6. Then 2 to the 2, we would store 4. And then 2 to the 3, we would store 0. So let's imagine we have this for every single element in our tree, where we have a logarithmic parent instead of just a linear parent. Now this, if we have a tree of 5,000 nodes, now for every single node, we would only have, I think the log of 5,000 is like 20. So we're having log n space instead of n, which is a huge improvement on a big tree. Now, so we can do this where we store these, but what if the node we're looking for isn't in one of these, right? Like if we're only storing the first parent, the second parent, the fourth parent, the 8th parent, the 16th, whatever. What if our node is like the fifth ancestor? So let's say we go 1, 2, 3, 4, 5. We're looking for this node right here, but we can only go up 4. Well, that's a problem because we don't have this parent. But what we could do is, let's say we do have, so we're looking for the 5th parent. So what would 5 be in binary? It would be like this. Now what we could do is, when we have this k, we can just check every single number in this k. So this number, this number, this number. And every time it matches, we can go up the right amount. And we can have some kind of counter. saying where we're at. So we can just say I equals 1, let's say. Or it would technically be, I think, I equals 0. Okay. Yeah, so it would be I equals 1 or 0. And let's say we're here. This k is 5, right? So 5 equals this. And we're at this node, and we're trying to get to this value. Well, we can just keep checking each value in some kind of, we just have a 1 shifted I times, let's say. And we can say if this 1 is in this k, so for 0 it would be in this k, right? We can even AND them together, so we can just AND this with this, which would be like this, and 1 equals 1. Because when you do a bit AND with a 1 with some other thing, if it's in the same index, it'll just equal a non-zero value. So we can just say if this is a non-zero value, then we can go up the right amount of parents. So if I equals 0, we can just say this is the 0th parent, and the 0th parent is going to be up here. So now we're at this value. Then we shift our I. Okay, we try to AND it again. We can't do anything. We shift our I again. Okay, we have a 1 again. And now our I is 2. And 2 means we need to go up 4 nodes in our tree, right? So 1, 2, 3, 4. But instead, what we can do is we have this array for every single node. So we have this array for 7 as well. So for 7, we'd also have a 0th parent, right? So going up 1, then we go up 2, then we go up 4, then we go up 1, we go up 2, we go up 4, so it'd actually be 1 here, and then the next one's out of bounds, so -1. Okay. So we have this, and we could say, okay, well, we're at 7, we need to go up 2, because if we go up 2 from 7, that would be the same thing as going up 3 from 8, because 7 is the parent of 8. So we can use the parent of our child, and we can keep going up, and this way, we don't need to store as much. For every node, we only need to store log n values max, and we can go up quickly. We don't have to go up one node at a time. We can go up in a logarithmic amount of time. So I know this is kind of confusing, so let's code it up, and I'll explain the code as I go. Okay. So first thing we need to do is we need to store this n value. Second thing we need to do is, for this picture, we need to figure out what's the maximum number we can go up. And so the worst case scenario, let's say we have n equals 8. The worst case scenario ancestors would be 1, 2, 3, 4, 5, 6, 7, 8. 8 ancestors. And how many times would that be in log? So we'd go up 1, we'd go up 2, we'd go up 1, 2, 3, 4. And then, so log of 0 equals 1, log of 1 equals 2, log of 2 equals 4, and log of 3 equals 0. So it would be 3. So what we need to do, but we also got to keep in mind that when we're going to loop through this log array, it starts at 0 indexed. So what you also could do, if you didn't even want to calculate how many logs you need to, like, you want to store the minimum number of one value. So technically, this log can be something like you can loop through 20 times, and then once you're out of bounds, it would just store -1s the rest of the time. So it would be like this. Once you run out of parents, it would just be like this 20 times. So that's what you could do. You could just hard code a log value that you're guaranteed to have your input in. But if you want to get exactly, roughly, how many numbers you need, then it would be something along the lines of like this. So we're doing a log base 2 of n, and then we're adding 1 because this is 0 indexed. So we want to make sure we might have some error where we're 1 off. So technically we could add maybe 1 or 2, but this would give you roughly the amount of logs you need, and then if you ever go out of bounds, you can just add a couple more. But then you're not using 20 logs when you could use a few. So now for this, what we need to do is initially we need to have an array. And for some reason, it's tabbing still. Okay. So we need to have an array here. And we need to have a DP array. So actually, I didn't initialize that yet. So this DP array, it's going to be called a DP array, but it's technically an array of all of these parents. And so what that's going to look like is it's going to look like this. It's going to be initialized to -1 because all we're going to do is we're going to have all the parents initialized to -1, and then whenever there is a non-zero parent, we're going to change those values. But that's going to be the easiest way to do it, and then we're going to have every parent that we didn't change just be -1. So it's going to look something like this in Python. So it's a two-dimensional array, and this is the columns. So this is going to be one row basically of the array is going to be -1 times self.logn. And so looking at this example, let's say we have this and our log is 3. So for 0, we're just going to have -1, -1, -1, -1. And then for 1, we're going to have the same thing, and so on. And so this would be the 0th parent, the first parent, the log 2, log 3 parent, and so on. Okay. So in this array, first what we can do is we can just initialize the 0th parent to the parents that are in this given array here. Because we're given the 0th parent, so like the 0th parent of 1 would be 0, the 0th parent of 2 would be 0, and so on. And now we have a nested for loop, and we're going to iterate through every single log. And so let me show you that, and I'll explain it. So this is log. Okay. So these log values are which parent are we on. So because we're given the 0th parent, this is the 1 parent, the 2 parent, and so on. And remember that the 0th parent, like if we have 5, the 0th parent is here. The 1 parent is, it's 2 to this power every time. So it's going to be up here. And so from this example, let's say we're at 8. The 0th parent's here. The 1 parent's here. And then the 2 parent is 2 to the 2, so it'd be here. And then the 3 parent would be out of bounds. So we're iterating through every single parent from the first parent to the last parent. And then we're iterating through every single node. And because these nodes are written in order, we're guaranteed that when we look for a parent, the previous parents are already going to be in there. And so what we need to do is we need to do this. And now I'll go over this code as well. So this is saying if self-dp I j-1 is not equal to -1, meaning this is the node we're at, and this is the previous parent. So for example, if we're here, let's say, we're at this node, if parent number 3 is out of bounds, then parent number 4 is going to be out of bounds because it's going to be even higher. So if it's -1, we don't need to do anything because the next parent is going to be out of bounds. And then we're going to need this. So it's going to be equal to, we're going to take its parent, oops. Okay, and we're going to show this with an example. So if we want its next ancestor logarithmically, we're going to take where is this previous ancestor located, and then its next ancestor. So let's try to go through this code and let's see what that looks like actually. So we're gonna let me see here. Let me draw out these nodes again. Yeah, okay. So let's say we have these nodes again, 0 to 8. So what I'm gonna do is I'm gonna have all of these nodes. So let's just say 0, 1, 2, 3, 4, 6, 7, 8. So these are the nodes, and let's just make an array for all of these. So in this case, they are 4 values, I believe. So let's just do this for all of these. Okay. And we're going to go through this, and we're going to try to see how this works iteration by iteration. So it's kind of annoying, actually, but it's okay. Okay, let's just put it here. So let's see what this would look like. Actually, instead of doing this, let me just probably write them out. I think that would be a little bit cleaner. Yeah. Okay, so let's just do that. So -1, -1, -1. Or actually, instead of even writing them in, let's just go through these things. So first of all, our first thing is going to be the parent is the initial parent. So for example, for 8, it's going to be 7, 6, 5, 4, 3, 2, 1, 0, -1. Okay. So this is the initial parent. Now we're going to need to go through the second parent. So for any time we have a -1 to start, the next ancestor up is always going to be -1 because we can't go up from -1. So this would be -1. Now the next parent of 1 would be, well, what's its initial parent? It's 0. And then what's the parent of 0? -1. So this is just, remember that parent 0 equals log, or it would just be this. And then parent 1 is 2 to the 1. And so this is how many we go up. Parent 2 is 2 to the 2. So this would be the node right above it, because it would be 2 to the 0, which would be 1. And then the second iteration would be 2 nodes above, right? So like in this example, the first parent would be here, the first ancestor. Sorry, the first parent would be here. Then the second parent would be here, and so on. So now we have to think about, okay, so we're here, we're at 2. Now, what is this parent 1 here? Well, it's 2 nodes above. Well, what does that mean? We have to go to its parent, and then we have to go to 1 node above. Because our algorithm is we go to the parent of the node, and then what's the parent -1 of that? So if this equals 1, and this equals 2, and this equals 4, then we're trying to find a parent, like the first parent here of some node, we go to its parent, and then we subtract 1 from this number. Or we don't subtract 1, but we go up to the previous logs, which would be here. So for 2, we would go up to 1, and we'd say, okay, what's its parent 0? Well, it would be 1, right? Yeah. And you can also tell this is all connected. So this would be the second ancestor, technically. And the second ancestor would be 0. So this is 0. Okay. Now at node 3, we'd go up to number 2, and then we'd say, okay, well, what's its parent -1, which would be 1. So this is just 0, 1, 2, 3, 4, 5, 6. Okay, so now here, this is log base 0, this is log base 1, or log 0, log 1. Now this is log 2. So log 2 is 4 here. So once again, we have to go up to its parent, and then from this code, right? This j-1, what's its parent? Now it's not its immediate parent, it's its parent in the step before. So the step before is 2 nodes above. So once again, if it was anything -1 is going to stay -1 because we're traversing up. But for something like this, for 2, because its previous parent is 2 nodes above here, because we're at index 2, you could see that this difference is 2. This would be 2. Now this is going to go up here, and it's going to say, okay, what's its parent? -1. Then 3 is going to go up to, what's its parent? 0. And then, actually, this is, I'm not sure if that one's right. So 2 is going to go up to 0. What's its parent? -1 for sure. 3 is going to go up to 1. And then it's going to say, yeah, so here's the other issue, is it's not going to say what's its direct parent. It's going to say what's its this value here, 2 above it, which would be -1. Right. So I hope that makes sense, because, yeah, like we're at this tree, when this value here is 2 to the 4th. So we have to go up 4 times. So 1, 2, 3, 4. So we go up to the previous node, which is 2 above, and then we're saying what's the node 2 above that, which is here. And then for 4, what's the previous node 2 above? Okay, what's the node 2 above that? 0. Okay. 5, previous node, 1. 6, previous node, 2. So, okay. Now 3, so this is 2 to the 8th. Or sorry, this is 2 to the 3rd, so this is going to be 8. So this is saying what is the node that is 8 ancestors up. Okay, well, once again, these are all 0. For 3, so we're at here, we're at 2 cubed equals 8. And then we're saying, okay, what's the number before this number? Let's go up there, and let's look at the child 4 up from there. So if we're at 3, or if we're at 4, we're going to go to here, and then what's the child 4 up? Okay, it's -1. Then here, we're going to go up 1, 2, 3, 4. Here, child 4 up -1. 5, -1, -1. And I think this is the first one that's not -1, so we go up to 1, 2, 3, 4, 1, 2, 3, 4, 0. Okay, and hopefully that makes sense. So this is, because we're at the 3rd level, this means 8 nodes above. So 1, 2, 3, 4, 1, 2, 3, 4. And you can see that if we were just to store every parent here, this would be quite expensive because this 8 would have 8 different nodes. While here, we only have 4 nodes, and as we go up in levels, we're saving ourselves way more space. So we can go down 8 more nodes, and we're only need to write 1 more value and so on. So our array is going to be pretty small compared to just storing every single parent. And so hopefully this is not too confusing. I know it's definitely kind of confusing. You can take a look at the code and see if it makes sense to you. But yeah, basically we're going up to its parent at the previous level, and then we're going, what's the parent of that? Okay, so let's write this kth ancestor and hopefully explain that. So if node is so it's asking, let me just double check here real quick. Okay, kth ancestor node of a given node. Okay, so first of all, if our node is invalid, I don't know if we're tested for it, but let's just say we are. So if node is greater than 0 or node is greater than n, this would actually be greater than or equal to, because our nodes are numbered 0 to n, so it can never be n as well. So this means our node is out of bounds. We don't need to check if our k is out of bounds because we can just check for that while we're in our k value. Okay, and I'm going to draw out once again how we get this k. So I'm going to code it up and then I'll draw a picture. So for I in range, self.log n node. So first of all, if we get this -1, if we ever get a -1 and we've traversed and we still have more to traverse, our only possible output can be -1 because we're already out of bounds. So we can just return here. Now this is the tricky part of the code that I showed before, I think. This would be 1. Okay. So this is what I was saying is we take the number 1, we shift it 1 times, and then we keep checking, is this equal to our k? Is it in our k value? It's not, is it equal to our k value? If it's in our k value, then we go up the right amount of time. So let's just demonstrate this using our example here. So let's say our k is something like 5 here, and we are at node 8. Do we want 5 or do we want something else? We can even have something like 1, 2, 3, 4, 5, 6. Let's just say our k is actually 7. And we are at node 8. And it's asking, okay, return the 7th ancestor of node 8, which would be 1, 2, 3, 4, 5, 6. So we should return 1, but let's see if we can do this using this array, using our faster method. Okay, so first of all, we check, is it out of bounds? It's not. Okay, cool. So then our I is equal to 1 here. Now we do this k and I shifted thing. So let's draw out what 7 looks like once again. So 7 is going to be this. and our I value shifted 1 is going to be, or our 1 shifted I times, sorry, is going to be this. So it's going to be shifted 0 times at first. And so we're asking, is this ANDed with this true? And like I said, because this technically is 0, 0, 1, when you AND these together, you will get 1. And so that is true. So if it is true, then remember we started at this node. If it is true, then go up the right level. So it's saying go to DP node and go up I amount of parents. And so we're at DP node, we're going up 0. So now our node is 7. So let's write this down. Let's make it a little bigger. Okay. So our node equals 7 here. And then we go to the next iteration of the loop. And we increment I. So I is 2. And we still have this. So if I is 2, it's this. Now it's asking again, is this ANDed non-zero? Yes, it is. Actually, let's do this. This ANDed together would be this. And so we do the same thing. We pick the node we're at, and we go up I levels. And so our I here is 1 now. So we go to node 7. Our I is 1, so we go up to node 5. And that makes sense because if you think about it, our 7 is broken down. What is 7 broken down into? Well, it's 1 plus 2 plus 4. We want to break it down into levels that we can traverse, right? So this 0 level is 1, this is 2, this is 4, this is 8. So if we break down the 7 into 1 and 2 and 4, and we can think about how we traverse. So we would go up 1, then we would go up 2, and then we would go up 4. And so even though we made it so we traversed the right amount of ways from this array to get to the number we need, even though we didn't have every single parent of every single node available. We traversed in a smart way. So let's just finish our example here. So we're at node 5. Now our I equals with 3. And so we have this k again. 3. 1 shifted left 3 times is going to be this. Or, sorry, it's going to be shifted left 2 times. So our I is going to be 2. So it's 0, 1, 2 because it's 0 indexed. So what's this ANDed together? Well, it's this. Okay. So now we have node 5, and now we need to shift it again. Or we need to do this DP node. So we're at node 5 here. Our I is 2. So this value is 2. I think I actually... Yeah, I definitely... When I was doing these numbers, I think this definitely needs to be a 1. So I think I screwed that up because this is the node that's 4 nodes higher, technically. So I think I did this math a little bit wrong somewhere where... Yeah, but whatever. So this node should be 1. I'm not exactly sure where I did the math wrong, but I'm not going to double check that, but you can kind of see what I was doing. I think I just miscalculated about 1 at some point. So we're at node 1 here, and now we return, and this would be node 1. And so let's think of the time and space complexity for this. So in our pre-processing here, we are creating an array for every single node, and we're creating a logarithmic number of parents for that node. So we have n nodes, and then a logarithmic number of parents for that node. And so that is going to be our time complexity. And then for this kth ancestor thing, it's just going to go loop k times maximum. And so that would just be n, because k is guaranteed to be less than or equal to n. So this is going to be the thing that actually matters in our time complexity. This is going to be faster. And then what's our space complexity? Well, it's the same thing as this top thing. In this pre-processing, our array that we make is going to be big O of n times log n space, because for every single node, we are storing a logarithmic number of parents. So that's going to be the space complexity. And so that's everything for this question. And I know it's kind of confusing. It was definitely confusing for me even to draw out these examples. And what I would recommend is, even if you're not super familiar with this now, I would recommend maybe storing this problem, trying to do this by yourself in a week or two, just to kind of, because if you just look at it once, this is not a super common algorithm. You're probably going to forget it. So try to look for it in a week or two, and maybe, like I said, they might have. Let me check here. They might have something. Okay, so let's see what we did wrong. I don't think we ever actually tried to submit it, so let's just make sure it all works. Okay. Yeah, so I would try to do this algorithm again, and then maybe use this algorithm for other similar examples like a lowest common ancestor, which I might do in another video, even though you could solve that using a simpler solution. But yeah, as you can see, I mean, this question was asked on Fang interviews, and if you were able to get this one without any hints, that would be super amazing in my opinion, because I think this is a very tough one. So I'll see you in the next one.